Okay, so the problem that we want to talk about today is this problem called chocolate packing. Okay, suppose you have you have a candy store, right? And the point is that you want to assemble 1 kilogram of chocolates. It's a lot, I know, but for now, let's assume that. Okay, and then the thing about the chocolates is that this chocolates at the store have very quality lah. Some are very good, some are so-so, whatever. Okay, and it turns out that there's each of the chocolates has a scale, can be rated on a scale 1 to 10. 10 is the best, 1 is the worst. Okay, and it turns out that each piece of chocolate has a certain weight. Okay, so the question here is how can you pack together, okay, 1 kilogram of chocolates, okay, so that you maximize the total goodness of the chocolates, okay, in the pack. Okay, so you can start by creating these abstract data types for chocolates. Okay, first you can, chocolate essentially has 4 things. It has got a filling, has a covering, has got weight, and a desirability. Okay, and very simple, we just use a list to basically represent the data. Okay, and then we use CAR, CADR, CADDR, CADR to basically access all the different attributes. Okay, so we can basically try to create a whole list of chocolates like this. So first chocolate is a dark caramel chocolate. Okay, 13 and 10. What's 13? 13 is the weight and 10 is the desirability. Okay, so your dark caramel is desirability is 13, weight is 10. Okay, milk caramel 13.3. Okay, dark cherry is 20, weight desirability 3, whatever. So you have a whole bunch of chocolates, okay, different kinds, different weights, different desirability. Okay, your goal obviously is to pack as many pieces as you can, okay, to maximize the total goodness of the set. Okay, so make a box. So a box, basically what you do is that a box, you have a list of chocolates, a weight, and a desirability. So the empty box is just nothing, 0, 0, because no chocolates, no weight, not desirable. Okay? And then, basically, if you want to get the chocolates, you can get this list, which is a CAR. The weight of the box is this number, which is a CADR. And finally, the desirability is the third number. Okay? So what can you do? To add a chocolate to a box, what you do, you cons the chocolate into the list, and then you add the weight of the chocolate to the total weight of the box. Okay? Very simple. Right? And we define the following also. We define a better box. Okay? If you compare 2 boxes, box 1 and box 2, okay, the better box essentially will compare the desirability of the 2 boxes. Basically, the sum of the desirability of all the chocolates in each box. Compare and then return the one with the bigger one. Okay, simple. Okay, so how do you solve the problem? Yeah, I've given you a problem, right? Yes? Right.
But could you know like what the deep what you can build is with no weight and no chocolate? But,
Right. So it's essentially one way of doing it is that you can do what? You can create every single possible combination of chocolates that can fit in the box. Check each of them, and then find the highest one, right? So and you said no weight, no chocolate, something like this. So essentially, you enumerate all the possible boxes, right? Basically, try every single way. Compute desirability, and then pick up. Right. So this is the kind of the brute force way of doing it, right? Okay. So you do. You can do the following, right? Now, pick chocolate weight, right? If chocolates, there are no chocolates, then you basically make empty box, right? If the weight limit is 0, you make empty box, because you know these are 2 basic cases, right? If you have no chocolate to pick from, or if you basically have no weight, you cannot keep any weight, then the answer is that there's no, the best you can do is empty box. Right? Now, suppose the chocolate weight, okay, of the car of chocolates, that means that you take the, okay, this chocolate, what is this chocolate? This chocolate is a list of all the available chocolates, right? Okay? Now, if you check the weight of the car of the chocolates, which is what? This is the first one, right? If the first chocolate, okay, if the weight of the chocolate is more than the weight limit, then you know that you cannot possibly put the first chocolate inside the box, right? Okay? Then what you do, you basically pick chocolates again, you cool down the chocolates and then the weight limit, correct? So it's simple recursion. So if this is a chocolate, the first one is too heavy, you basically throw the first one away, you keep doing it the second one. Now suppose it's not too heavy. Then remember the count change, right? What is the general idea? You have the first one, at least one of the first one, or none of the first one, right? Okay. So then you do what? Okay. You basically pick the better box, okay, of none of the first kind, okay, or at least one of the first kind, right? Same as this is similar to the count change, right? Essentially, you pick chocolates, cooler chocolates. So none of the first kind means that you just cool down the chocolates, okay? And then other than that, what you can do is that you can add the first chocolate. So add the first chocolate, okay? And then you pick what? You pick again. Basically, you minus the weight limit of the first chocolate drawn, minus the weight of the first chocolate from the weight limit, and go some more. Okay, so essentially this is exactly count change, right? Pretty much the whole point now is count change asks you how many ways that are changing this thing. This is kind of asking you how many ways are you of picking this thing, and then figuring out among all the ways which is the highest one, right? Okay, simple solution. Now, what's order of growth is? Sorry? Exponential. Why? Because you know that this thing is branching out. Right? Every step that is not null or base case, right, is branching out. Exactly like count change, right? So this is some kind of exponential order of growth. Okay. But the thing to realize is that there are a lot of repeated computations. Okay. Obviously, the first thing to think about is memoization. Right? This is what I taught you last week. Okay. So we can do this, right? We can do memo pick chocolates. Okay, memorize 2, right? And then we can do this thing similar. Okay, this code is exactly the same as this code, pretty much, except that I have renamed it memo pick chocolates, and this memorize 2. Okay, and this is what I did. Okay, is it okay? It's not quite okay, but okay. Why use memorize 2? Because last time, we actually use n and k, okay, to look into the table when we do the what's that thing called? N choose k, right? Okay. So now we list chocolates. So we notice that it's not really the list of the thing is that where's the memo pick? Okay. So the memorize 2, you need to change this because memorize last time we actually used 2 numbers n and k, right? Here we have chocolates, okay? But we notice that it's not the chocolates that matter for now. You just keep track of how many chocolates you have left, okay? So remember, it's the same as the how many denominations left, right? Okay. So here you use length of x instead of the x. Okay. So let's quickly do a recap of what we discussed last Friday. So memorize the two key ideas, 2 key steps. First is to write down the procedure to perform the required computation, which is a normal recursion. Okay? And then the next thing you do is that you add a wrapper that stores the result of the computation. Okay, because what happens is this, right? You have you have some kind of things like Fibonacci or whatever, right? And then it goes down and then you do this thing, right? What you do here is that you add a wrapper because what happens is that when okay, typically you call f. Okay, now you call something else memorize f. What it does is that in between the memorize and f, right, it inserts a layer where what this layer does is that first of all it goes to the table, checks whether or not the table answer is already computed. If it's computed, it just returns the answer. Okay, if not, then what it does, it actually goes down and computes f. Okay, and then when it returns the answer, it will store the answer in the table before it returns the answer to the user. Alright, this ensures the next time if you've done it before, when you look again, it's there. Right. So typically lookup must be done with a constant time lookup table. right? If not, then you have a problem because you did not be better than before. Okay. Now, so you just have to make sure that when the key thing to realize is that when you actually wrap the procedure, make sure that recursive calls must go to the wrap version and not to the original version, because if not, then you won't do the lookups and then you will not save anything. Okay. So memoization is a simple idea, right? It's just to remember stuff you've done, so that you don't do the same thing twice. Okay. Now it turns out that the method that we use to implement memoization, this idea of wrapper is very, very important. Okay. There are many things you actually do to what you can do is enhance the functionality of an existing function. Okay. And this thing is called design pattern. Okay. There will be many more design patterns that you learn, hopefully, along the way. And the key idea here is that you introduce an additional layer of functionality. Okay. That basically also uses the original procedure to do the old work. Okay. This one you will actually see some of it in the OOP problem set, I think, right? So object problem set, what happens is that normally you have a superclass. Okay. Then there's a method in the superclass. Then normally what you do is that you create a subclass of the superclass with the same method name. Okay. Then very often what happens is that you will call this method in the subclass, right? And the subclass will call the similar method in the superclass to do something, return to it, and then it will do something else. Okay. So this is actually quite a common concept. Okay. So let's take a look at memo choose. Memo choose is the HSK that we did last week. So it turns out that at the end of the whole computation, suppose you do choose 9choose4, choose 9,4. It turns out that after the computation is done, this is what the table of values will look like. This is what it looks like, because okay, F means it's not filled, right? And the rest of them are filled as you go along. Okay, so this is what it looks like. Now, if you think about Pascal's triangle, okay, it looks like this, right? You don't remember Pascal's triangle from the DG, right? Okay, it looks like this. Now, since that looks a little bit off, I don't know why. Okay, so basically the way this particular table is set up is that each entry here is the sum of the one that's directly above and the one that's to the left, right? Okay, this is off. I don't know why. I think it's just alignment issues with this PowerPoint version. So it's actually 3 plus 1 is 4. So essentially each of these entries is the sum of the two entries. Okay, so dynamic programming, what does it really mean? Okay. Okay, so the idea is this. Okay, I recall, memoization, what it does is this. Memoization essentially intercepts the call. Okay, and it will basically store the answers in the table. So just now, you've seen that the NCHOOSE table looks like a certain form. Okay, so essentially what happens in memoization is that you're filling out a table. Sort of, okay. Now the question now is, why don't we just fill the table directly from the bottom? Okay, so what memoization does is that basically it gets a certain value. Okay, then it tries to basically find the next value and so on and so forth. At some point, it fills the table upwards. Okay. So the name for this idea is called dynamic programming. Okay, and I think JT asked, right, which is better, right? Memoization or iteration, right? Yeah, actually what you're saying is the iteration thing is not iteration. Iteration is actually dynamic programming. Okay, so what's the order of growth now if you do this filling up table from the bottom? M times N, okay? Okay, whatever it is, it's the size of the table, essentially, right? Because the table is of size N times N. It takes only, you need to fill each thing once, so it will be M times N. Okay. Dimension is smaller. Okay, why? Because I said it already. Okay, so DP choose. So this is the this is basically how you would do choose. Okay, so just now I mentioned we saw NCHOOSE last week, right? So this is essentially how you would do it. Okay, so you create a table. Okay, where is oops, I can't get to the fit. Okay. So this is first you create a table, okay, n by k plus 1, okay, and then basically define choose to be this. If n is less than k, obviously you can't choose. The only way is 0, okay. if n and k are the same, it's 1. If k is 0, it's a 1. Okay, and then this is actually how you add, right? So n choose k is actually what? N minus k choose k minus 1 plus n minus 1 choose k. This is the one that corresponds to the one that's n choose k, n minus 1 choose k plus n minus 1 choose k minus 1, right? Okay, and then basically you can use the table ref to reference the table. Okay, and this is what you do to store values into the table. Okay, this is not very important. So let's take a look at what's more important is how do you adopt this approach to solve the chocolate packing problem. Okay. Okay. Now, so let's take a look. Okay, remember that dynamic programming is really about filling out this table efficiently so that the total time complexity is equivalent to the size of the table, right? So, okay, the question now is, okay, so this is important, very important. First of all, if you see problems, okay, that is something like count change. Basically, they are exponential in nature. Okay, number one. Number two is that if you notice that there are many repeated nodes, that means that there are some nodes that are the same. Right, like Fibonacci, oftentimes there's a lot of Fibonacci, like on the left side, right side, a lot of repetitions. Okay, when this happens, right, essentially you can either use memoization or you can use dynamic programming to solve the problem. Okay, to reduce essentially what is an exponential problem into a linear one. Okay, quite obvious, right? Now, so the key is this. The key is to ask yourself, okay, the key is that you need to fill a table. So the key question is, what does the table look like? So for chocolate packing, what does the table look like? Okay, the table, okay, this is obviously a 2D table, right? Okay, so what is one dimension? Weight, okay. One is how much weight. Weight is normally this one. Okay, the vertical weight. What's the horizontal one? How many? No. Okay, so one is the weight. What is the? No, not chocolate children. The list of chocolates you can choose from. Okay. Similarly, okay. Remember, count change is what? Count change is one of them is the total amount, right? What's this one? This is the types of coins, right? I say again, so count change has the same table, right? One is actually the types of coins, denominations, and one is the weight. It's not weight. One is the amount. So in chocolate packing, okay. I mean, you can flip it around, but one column will be the types of chocolates you can choose from, and one will be the weight. Okay. So it's a table or list of chocolates versus weight. Okay. So each entry in the table is what? So each entry in the table represents the optimal packing you can do for that weight and that list. Okay. Observation. First of all, no chocolates. Answer easy, right? No chocolates, then all empty. Correct? Okay. The other obvious thing is what? No weight, then obviously answer is also all empty, right? Okay. Otherwise, the thing is that if the remember just now you saw the better box thing, right? The better box. So for a given entry, what is the best way of doing it? It is either one more chocolate. Okay, what I'm saying here. Okay, the answer for a list of X types. Okay, that means you think of it as an entry inside the table. Okay, it is answer the better version of what? You compare two things, right? You compare basically not having this thing. Okay, I think it's easier to see the table. Okay, so let's look at the table. The table is like of the following form, right? Basically, you have all the weights, okay, in the vertical axis, and then essentially this one tells you how many chocolates are there. Okay, so first of all, you don't use the chocolates at all. Okay, So if there's no chocolates available, the best thing you can do is nothing. Okay? Now, suppose you have one chocolate A. Okay? One chocolate A. Right? Weight 4, desirability 2. Right? Okay. Now, we know for a fact that, okay, so you know that this is true. Now, this row here is all going to be empty also for sure, right? Because this has no weight. Okay, so this whole row is all empty. I mean empty list. Now, then the question now is this, for each of these boxes, how do you fill? Now, in this case, it's quite obvious, right, that basically from A, okay, now this one is all 0, so what happens is that you go to 4, then you can put chocolate inside, then you put A, and the desirability of this thing is 2. Right, you keep going down to here, there's A, and then it's 2 pieces and so forth, right? Now, so this one, what is this A? A is actually check the top and check the left, okay? So we know that the left, the desirability is how much? 0, right? And then you check basically the 4 up to here. Okay, from here to here you add 1A, which is 4, and then desirability will be 2 more. So here, so essentially desirability of this thing is 0. The desirability of this thing plus 1 chocolate is actually 2. Okay, and you compare it to this one. This one is actually 0, so you choose the larger one, which is plus A. Okay, similarly, this is actually this thing plus A, and this is actually still compare 2 to 0, and then you get this. Okay, so again, this is very confusing. Let's try again. So what happens is, in each of these entries, you have 2 choices. Okay, one choice is not to use the current chocolate, which means what? You check the guy on the left. Okay, the guy on the left is the best possible thing you can do without using the current chocolate, which is A. Okay, the one that is here is the one where you use at least one of this chocolate. Okay, see, if you see, the idea is this: if you use at least 1A, then you would move up, you leave current amount minus A. This is the best you can do. So this is 0, this is 0, but this to here is actually plus 2. So you pick this one, which is A. Similarly, this is the same. Okay, this is more, now this is less obvious. Okay, so now I add a new chocolate, which is B. Right? So before 3, basically there's no way I can put any chocolate because this is 5, this is 4, they're all zeros. Okay? Now at this point, okay, there are 2 possibilities. One possibility is that I use one more of this of B, which I cannot because I cannot. Right? Then I will compare to this guy, okay, which is A. This is what? The best I can do without using B. Now, once I reach here, basically I compare 2 things. I compare use 1B versus don't use B at all. Okay? And obviously use 1B, the answer is 3. Use only A, answer is 2. So B is superior, I use B. David, cannot. Okay? So the general idea here is, go and practice and write this DP chocolates over the weekend. Okay? So the idea is that DP oftentimes requires more computations, because if you look at this list, okay, you look at this thing. Okay, this is memoization, right? Okay, this is what happens at the table after memoization happens. Okay, for choose K. Okay, you see that a lot of false, not a lot, some false, right? Which means the lows and never float. But if you do DP for this thing, right, you end up filling everything because you don't know what to fill it. Okay, so in that sense, DP you may end up filling more entries in the table. Okay, and DP requires you to know exactly what you're doing when you are filling the table. You must know exactly how you go and how you compute. Okay, because the table can be filled in a certain way only. Okay, but then the interesting thing is that DP, if you are smart enough, right, in how you're doing it, you can require substantially less space. Okay, one example is what JC says, right? She asked about this memoization of Fibonacci, right? Fibonacci, you know that you can either use memoization like last time, or there's actually an iterative way of doing it, right? Okay? Iterative way is actually DP. So the question here is, which is better? The two are equivalent. Except that if you are smart enough, right, you use less space. So Fibonacci in the extended style requires only two units of space. Okay, so that's actually all I have. Okay, the only concern now is whether or not you understand this table. Any questions? Good question. What's the order of growth? N squared. Okay, the only thing about this is this, right? The how much time will it take? The amount of time it takes. Okay, let's just get it straight. This is how it works. The first thing to understand about DP is this: is that you essentially need to get some value somewhere. Okay. And this table is normally a 2D table, maybe 3D, whatever, some D table, some tables. For now, just say 2D. So the idea here is that you can build these tables by essentially sequentially filling up the entries. You fill until you reach this level, this particular entry, you're done. This answer. The rest, the one that's beyond and above, you don't care. Okay. So the time taken, right, is the time taken to fill the table. Okay. So if this is n by k, then the total order of growth will be n by k. But typically, you know, like okay. So if you remember count change, right? Count change, there are two variables. There is D, which is the number of types of coins, and there's A, which is the amount we change. Okay? So typically the D we consider it to be fixed. So it's order A. So in this case, this will be order N. Right? Because you consider the number of types of chocolates to be kind of constant. Yes? Okay? So the general, let me quickly sum up this whole thing. It turns out that DP and memoization, they are quite equivalent. Right? In the sense that pretty much they do the same things. It's just that you can think of DP as a bottom-up approach. Basically, you have a table. Okay? What you need to do is reach a certain point at the table. Okay? Normally the beginning rows, this row, the first row and the first row there are obvious. They're all zeros, all empty or something. And then from there, you can just really fill out the table sequentially to reach this point. Once you reach this point, you're done. This is DP. Memoization, what it does is that memoization essentially computes this number. Okay? But when it does computation, whenever it finds a number, it will fill out the table. So essentially, memoization, you can think of memoization as filling the table from top down. Okay? Exactly what sequence you fill up the table it depends. DP typically is filling out the table from bottom up, and you quite sequentially fill out every single entry in the square. Okay? Typically, that's how it works. Any questions? Okay, so which is better? I think from the perspective of basically from scheme, if you have this table available, it's easier to do memoization, sort of. Okay, but it turns out that if you want to program, like, you know, without using a table of that sort, right? If you want to do C programming or Java programming, use an array. Basically, it might be easier to do dynamic programming because you just do loops and you fill up the table kind of sequentially. It's not table, the arrays. Okay? Questions? Use a stack. Use a stack for what?
Then a stack to store what you are currently computing and keep on adding the things that you need to compute. Then after that, go to the last one and compute. Then after that, add that into the array and then go back.
You could do that. Okay. Any questions? Okay, so today is actually a relatively short lecture. And actually the good news is that this is, okay, again, these concepts are very simple. I mean, the concept is kind of simple and obvious. The problem is application. Okay, the challenge is whether or not you can take this thing and go and actually apply it. Okay, the way to do it is actually to go and try problems. Essentially, you take those numbers, like those problems like Fibonacci, count change, all those problems that require this kind of exponential nature. Okay, and try to convert them into DP or memoize. Okay, and essentially just, you know, figure this out by yourself. Okay, so nothing further, then the whole afternoon will be, I think, testing for the robots, and tonight we have a competition. Okay, after this, the TAs will follow me to go and collect the board and everything. Alright, any other final questions? Okay, if not, then I wish you all the best for tonight. I'll see you guys in this evening. Okay, thanks.
before already, so it's such a.
I don't know is it.